Well, I'm here with Bob Greenyer, who I've just got to introduce myself to just before we began now. And he is an engineer, a researcher in the field of LENR, which we're going to get into. I think it's a very promising field for nuclear energy. We're going to get into kind of a lay of the land and introduction to this space. So thank you for joining me, Bob.
Hi, David, and thank you very much for having me on.
Well, very good. Now, first, tell me a little bit about your organization, the Martin Fleischmann Memorial Project. Martin Fleischmann was a huge figure in this space, right?
He was, and sadly, I never got to meet him. I saw the original press conference. I'm old enough to have experienced that, and the sort of supposed fall from grace of the two electrochemists, and it struck me as odd at the time, and I was always interested in energy. But how the project came about is quite simple. There was a little bit more noise in the field in 2011, and got interested that had no connection with each other. And we took it upon ourselves to arrive in South Korea at what was then the semi-annual ICCF 17. So this is the International Conference on Cold Fusion or Condensed Matter Nuclear Science. And this was held in Daejeon in South Korea. And I just sat down and I listened to the presentations and I realized a number of things that I understood a lot of the science. I saw that there was a lot of commonality between people's work. There was clearly something going on that was of interest and should be further studied. But the scientists were getting old. And in fact, sadly, Martin Fleischmann, who was intending to be there, had died 3 weeks previously. So I kind of missed never meeting him. Well, I never met him, rather. The people that were having some success would get investment, and then really they close themselves down. And on the flip side, the scientists were they all wanted to succeed, and there was about 130 different theories, which obviously couldn't all be correct. And everyone wants the Nobel Prize, and so I've been through my career, I've tried to look at radical ways to solve a problem, which are unconventional and so forth. So I thought, well, if the problem is right from the beginning, the get-go, is there is an absence of truth that people can believe in, how can you demonstrate to people in the wider community that what is going on is real? In a way that is accessible to them. And I thought with the power of the internet, surely we should be able to do this online in real time, so that they know what we're going to do beforehand. They could observe the experiment being built. Anyone in the world could comment on what should be done to get the experiment right, even old hands in the field and newcomers with fresh ideas. Then once the experiment protocol and experiment itself is built, we could conduct an experiment and data stream live through online feeds of the data and charting, and also through YouTube. And people could communicate with us real time whilst the experiment is being conducted, and actually suggest things that should be tried during the course of the experiment. But that they would get access to the data, so that there couldn't be any cherry picking of the data going on, and it would be the crowd, the public, that could even look at the raw data and see if there's anything meaningful in there. And in fact, that's what we set out to do. There was two things that we needed. We needed someone to share their technology, because none of us had our own technology. We needed to be fairly sure that it was going to work, and we also needed the ability to publish live on the internet, which it wasn't even available from the mainstream providers of data acquisition systems at the time in the way that was going to be affordable for us to do. And it had never been done before. So we called this thing Live Open Science right from the get-go, and we called the project Martin Fleischmann Memorial Project because unfortunately he had died 3 weeks previously, and we thought, well, let's call it that. It's the right name for it, and can we get him some sort of credibility reset through this methodology. And so what happened was Francesco Celani, who was presenting there and had actually brought along a reactor, and it was showing apparent excess heat. And he had also showed this a week or two before at National Instruments Week in America, and it was producing excess heat there. And he was very open. So he worked at INFN, which is a nuclear group, government funded in Italy. And he said, yeah, okay, you can have access to my wire. Here is the drawings. And we worked with him. And it was five of us, Tyler Hooligan. I can't ever say his name properly. It was Ryan Hunt. I'm gonna struggle to remember everyone's name now. Matthew Villat, and Nicholas Chavan and myself, Bob Greenyer. We set up this project, and we went off, and within a number of weeks we'd failed the first attempt because we changed something, which is a fundamental mistake that everyone makes. They always think they can bring something to the table. But to be fair to us, the claimant had said that they were going to change the outside tube of the reactor with quartz from borosilicate, and we decided to do what he was going to do next, and it didn't work. So when we went back to his original protocol with this normal sort of borosilicate glass, we launched an experiment on the 12 seconds past 12 minutes past 12 on the 12th of the 12th of the 12th California time, which I thought was a good date and time to start an experiment. And it produced 12.5% within 2 days or a number of days. And I presented that in Rome.
12.5%. What was that?
12.5% excess heat based on calibration. And so that for us as a group was, it's like is it an inoculation? I don't know. It's kind of, once you've seen it, you can't ever go back. And whilst it's not what.
Do you have any demonstrations or visuals you can show us that might, like a model or at least visually paint the experiment for folks who are new to this?
So essentially what was taken was constantan wire, and this is a copper nickel wire that's it's 60-40 mix. And the reason it's used is because it has a very consistent resistance over a wide range of applied power. It was heat treated and it's called joule heated. So it was put in air and along sort of like a meter of it, and then it was pulsed with high intensity power such that it heated up very rapidly, and then the pulse was turned off and it cooled. And this produces an oxide layer. And as the oxide layer builds, it folds and it builds and it folds and it builds, it folds. And then he treated it with various chemicals, which are all in published papers that Francesco Celani has published. And then we take this wire and we put it on some mica, which turns out that it might actually be active in the overall heat producing system as well as the borosilicate glass. So it's on a mica support. So it's kind of like a heater that you would have, those old kind of heaters you might have in your bathroom in days gone by, an infrared type of heater, and in a glass case, the glass in this case being borosilicate. And what we were doing is we were measuring the temperature of the glass on the outside, and using some scientific equation called Stefan-Boltzmann, which allows you to calculate the overall power that you're getting in thermal power. And we were doing that with a control wire, which wasn't this specially treated wire, and with the actual specially treated wire in a hydrogen atmosphere at 3 bar. So that's 3 atmospheres of hydrogen gas. And so the control produced a line, and that was used as the basis to calculate what potential excess was being produced. Now, what we saw was below what the claimant had seen, but it's 12.5%. And bearing in mind that if the hot fusion reactor works in Europe, ITER, then they're never going to be creating excess electricity. For a very small period of time, they might create excess heat, but that's got a long way to go to get that to electricity. And so this is a tabletop thing. And then as the experiments progressed, we thought, well, maybe there's something that's changed with the pressure or something. So we had like the same cell, but in a line. So we had a control one on one side with the same pressure, and then an active one on the other side. And we did a comparison, real-time comparison. And when the data was shared, it was all shared live and streamed on the internet. And in a lot of cases, it was the crowd that identified important parts of the data for us to look at. And it was then a year later, or roughly a year later, in October 2013, when we had this dual cell, and one side of it had a leak in it. And what happened over a number of days, the pressure would drop from the operating pressure of 3 bar down to atmospheric pressure 1 bar. And we would have to recharge it with fresh hydrogen. And what we found was that Mathieu Vallat in France, where the lab was at that time, we had also a similar experiment running in Minnesota in the US, Hunt up there in Pine River. But the one in France, this leaking one, when Matthew recharged it with hydrogen, what happened was we had a Geiger counter outside of the cell. So you had the wire, then you had the hydrogen gas, then you had the borosilicate glass, then you had an air gap, and then you had your Geiger-Müller tube. This was recording almost a tripling of radiation counts, which took a minute and a half or something to settle back down to a normal level. And this is interesting because you wouldn't expect this to be beta particles, and you wouldn't necessarily expect it to be gamma particles. That shouldn't be happening, not neutrons. So how was this device measuring this? And it did it every time. When we put the fresh hydrogen in, you got this radiation signal being recorded. So I was very excited by this. I stopped what I was doing. I flew down to France. I saw the experiment replicated right in front of me. We published videos surrounding that and information surrounding that. Then what happened was there's a scientist called Jean-Paul Biberian. He's one of the luminaries in the field. He's written a very good book recently. I can't remember the name of it, but go and look up Jean-Paul Biberian. I think it's Cold Fusion in all its forms. And this book, this scientist took some of this same type of wire and did a test. Within 24 hours replicated our finding. Now, when you replicate something yourself, that's looking like science. When a third party replicates it within 24 hours, that is science. And so this was radiation being produced, some form of radiation. We don't know what at that stage. As I said, it kind of like, what kind of radiation is it? Because it's there and then it's not, and it's only during this transition in temperature and pressure. We started getting all of these reports from around the world of people in the field, things similar in the past, in a wide range of completely different low energy nuclear reaction cold condensed matter nuclear science experiments. And so this was when we got the interest of some people that we didn't know who they were, but they were certainly interested in helping us. So those two things in December 2012 and in October 2013 were really transformational in my own personal life, in terms of, this is what I have to do now. And many of the people were inspired to get into the field and start taking it more seriously. So we had excess heat within our second experiment. And we had multiple experiments after that. Then we had this radiation. Now, the excess heat is almost trivial to explain away. You could always find an excuse for why it's not. Even when we had it in an isoparabolic, like two water vessels, and we had a control and an active, and there was apparent excess here there. Still people would try and find a way. But when you're seeing radiation and you can control when that radiation occurs, and then someone else, a third party, replicates that within 24 hours, it's becoming very difficult to argue that there's not something going on that's very interesting. And what we learned is that the most important data in this field is actually radiation and transmutation. And over the last several years, we have discovered in a number of systems, this is a discovery to us, but as we have found out, it's not a new thing in the field. In fact, Thomas Barkler, is it Thomas Barkler? Yeah, I think it's Barkler. I might got his first name wrong. But he discovered characteristic X-rays, but at the same time, he discovered this thing called J radiation, and this was in the early 1910s, I think. And he got the Nobel Prize for discovering characteristic X-rays. But this J radiation was higher in energy than anything that you could get from the inner shell, the K shell of an emission of a atom. And so that radiation, he spent basically the rest of his life trying to find out what it was. And it turns out that we might be actually seeing this radiation, and this radiation is extremely interesting, because I think the first time it was observed was in the 1950s in Russia, when they were producing apparently a active. I think I'll find the name for you right now, but it was a palladium deuterium heater. And the palladium deuterium heater, oh, sorry, the palladium deuterium heater was also creating this type of radiation that was causing radioisotopes to change their decay rate. But that wasn't made public. But since then, many other observers have observed this phenomena of this changing of decay rate. And I think it was in the 1990s, there was a lot of research done both in Japan and in Russia, and they found these tracks, which were eventually coined by one Leonid Oryzhkev, which is a Russian researcher, when he was exploding metal foils in water of various weights, and he called it strange radiation. And this radiation appears to be able to cluster into anything from a sort of spherical blob to bead chains to things that look like buckyballs, to things that end up looking like a pseudo-magnetic monopole. And they actually take the form of almost like a sliced mushroom on an X-ray film. Oh. And it's absolutely fascinating. And this radiation has been shown by Oryzhkev to be able to, what he did in one experiment is he actually he had two metal foils of iron 57. And iron 57 is a rare isotope of iron, and it has a nuclear magnetic resonance, which is well known. And he had this 0.7 of a meter away from his reactor, one at 90 degrees to each other. So one was 90 degrees in one plane, was 0.7 meters away in one direction, and then in 90 degrees to that was 0.7 meters away in that direction. And they had two magnets on one of them had the north pole attached to the back of the metal, and the other one had the south pole attached to the back of the metal. And the idea was this radiation a magnetic charge? And what he found was that when he analyzed a control piece of iron 57 sheet and the ones that were respectively on the north and the south pole of a normal magnet, he found that it positively or negatively changed the fine magnetic moment recorded in the nuclear magnetic resonance when he analyzed it after exploding this metal foil. And these metal foil experiments were fascinating. So, for instance, they use titanium. Titanium has a lot of an isotope, which is a type of titanium that has a different number of neutrons and protons in it. Well, actually the same number of protons, but different number of neutrons. And the titanium 48 was very abundant. And what happened was the titanium 48 was lowered from its natural ratio, and other elements either side of titanium were formed. So you had in this experiment both transmutation going on and the emission of this radiation that was able to act in a way that it looked like it was magnetic charges. And that's do you have a question? Sorry, I've been talking.
Oh, no, I'm just soaking it all in. So can you explain that a little bit more, how it was acting like a magnetic charge? Can you explain that?
So basically, if you imagine a normal magnet and you split it in half, the halves will still have a north and south to them. Yeah. Now, these structures don't appear to be real magnetic monopoles. So you have electric charge, right? And that has a positive and a negative. So a proton would have a positive electric charge, and an electron would have a negative electron charge. And if you had a buildup of, say, electrons, you would have a high, like, negative electric charge on something. Now, Paul Dirac, I think in 1931, wrote a paper based on quantum mechanics and said that really there should be the symmetry in out there in science where you should have a thing called a magnetic charge as well. So you would have like just norths and just souths. Well, no one's ever observed this, but these clusters of strange radiation, these superclusters of strange radiation, they seem to be able to form something that can act as a virtual magnetic monopole. And there is a patent by Boyd Bushman, who worked for Lockheed Martin, and he found that if you take magnets, standard like neodymium magnets, and you arrange them in a cross, for instance, with all of the souths pointing into the center point and held there with a metal framework, say aluminium, that is non-magnetic, and then on the cross, if you take the opposite axis, so you've got a cross, and then you're taking the other axis, you put another one with a south, but on the opposite side you don't have it. So if you can imagine, you've got the center points of a cube, and on every center point of a cube you've got a north and a south, but always the south is pointing to the center of the mass, the center of mass of that cube. But on one side only you do not have a magnet. You will get a magnetic beam coming out of there. Now, depending on whether you have it all south, it'll be a south magnetic beam, and if you have all the magnets turned 180 degrees, you will have a north magnetic beam. And this is like a virtual magnetic monopole. And what it is your other pole is suppressed, and you get this beam of magnetic field coming out. Now, that's in his patent. It's just one
Boyd
embodiment.
Bushman. I've seen the interviews with him. He's an interesting guy.
Yeah, so you can go and find this patent. So look, Boyd Bushman,
magnetic. He passed away a few years ago, right?
Yeah, yes, and it's a great shame, because he was a very interesting character. So, but basically, this is a very simple arrangement. Now, you could have thousands of magnets around the axis, and then you could have increasingly small axes. And there's a guy called, I can't remember his name, but he has this thing called the primer fields. You can go and look that up on YouTube. And effectively, he's taken, whether he knows it or not, the Boyd Bushman pattern and taken it to the nth extreme. And the shape that he creates are these bowls. And the bowls produce a field that's mostly going in one direction. And this is essentially the same kind of structure that you have that's produced naturally by magnets, because these things appear to be sort of magnetic, the individual quanta of them.
But so interesting. I have a friend of mine who comes on my radio show named Dr. Weiping Yu, and he's a physicist in the aerospace industry, and he has insisted to me, and he's made a great case, that every particle is made up of dipolar magnetic particles. So he's got his own view of physics that's kind of radical from the orthodox view, and he's always insisting that it's that he does not accept like an orbiting electron. He thinks it's just a magnet, and every protons, electrons, and there's no monocharged particle. Everything is a dipolar magnetic particle, and they're just different arrangements that create the structures of the different elements that we see in the universe. So.
And there's no reason to say particularly that is wrong. And what we know from physically doing this at the macro level is that you can create something that looks like a virtual magnetic monopole, but not in the truest sense, that there is one pole that is suppressed. You can physically do it with magnets, and this is the basis of Boyd Bushman's pattern. But what you observe in things that are of various quanta scales, and they are quite physically large, is that these structures form from this radiation that comes out of these condensed matter nuclear reactions. Now, let's assume you can create something akin to a monopole. There is a paper that was produced, which was in a peer-reviewed publication by Bogdanovich et al. At the Moscow Nuclear Physics Institute. And this was published, I think it was in 2019 or 2018. But anyway, he's observed these things where they have a water jet, and then they do high current, very fast discharges through the water jet to a metal substrate. And then after the experiment, they take the metal substrate out, and they observed on video and captured video of these toroidal structures glowing, like plasma-like glowing, with a little tail. So you can imagine it's kind of like a big fat, when you're wrapping a quote, you have like a little character there. It's kind of like how should we put it? Like a little tadpole with its tail bent. Yeah. it's kind of like that, but they do assume that it is a kind of toroid, and they see these things moving around under optical microscope and glowing 2 days afterwards. Okay, and these are plasma things on the metal. Now, I've been told by other parties that they've observed these things 1 month after an experiment. Okay, and they're glowing. I mean, they're on a piece of metal. How on earth is this happening? But also in those same experiments, they observed these, and this was published in again in that same paper. They observed these clustering into crystal-like structures and moving around on their own axis, each of the subsections, and the whole thing moving around on an axis. And if you imagine these structures moving around on a piece of metal, they may create the kind of strange radiation tracks which we have observed, which are incredibly varied. They are incredibly varied. And these glowing objects that they recorded on film, and in fact, we appear to have observed one using a standard induction coil, or rather another party has appeared to have observed a similar observation using a standard induction coil, sprayed water and a modified spark plug, a slightly modified setup to get the same kind of crystal-like structure of what Winston Bostick called in the 1950s plasmoids. And in his publications in the New York Times, not New York Times, the Sun, I think, in New York, and in international press, he said that these structures that we've observed in the 1950s, which he was publishing in, I think, 1957 or 1959, these structures could explain not only every scale of everything in the universe up to entire galaxies, it could explain everything down to the finest parts of the internal structures of the atom. And so something is going on when you have these extreme changes in disruption caused by, it's essentially what you would call a dielectric barrier discharge, where in the case a spark gap, the dielectric is the air, and you are building up a lot of charge, and then there's a cascade breakdown. And what you're doing is you're getting a lot of coherence and a lot of monochromatic formation of electrons, and these cluster into these toroids, and these toroids are relatively stable. And one author, Lutz Jaitner, using quantum mechanic calculations, he's calculated that these things that Bostick observed, that Tesla would have observed in the late 1800s, and that a guy called John Hutchison definitely will have observed, and the people that followed him. These things, these toroids, which a guy called Kenneth Radford Shoulders, who wrote a book having tried to study what John Hutchison had done. These things, according to Lutz Jaitner, presented at ICCF 22 last year, and you can go and see the video on our channel. That's the Martin Fleischmann Memorial Project channel. Look up Lutz Jaitner. He calculated that it's effectively like a lightning strike, but it's a lightning strike that's folded in on itself. So it's effectively a pinch plasma which is superconducting, and this causes the magnetic field that's created by this pinch plasma pulls in the electrons to such a point that they get to such a fine level that they're effectively only stopped by the electron degeneracy of they can't go in any further because the Pauli exclusion principle, they can't get any closer. But what you get is you get a magnetic field in that pinch plasma of 50 million Tesla.
Wow.
And so when you go to have an MRI, a magnetic resonance imaging, at your local hospital, maybe you need something looked at inside your body, they're typically sort of 2 to 3 Tesla, okay? Right. And you have to take everything metal off, otherwise it's all going to fly in there and become part of the apparatus and cause it problems. So this isn't 3 Tesla, this isn't 30 Tesla, this isn't 30,000 Tesla, it's not 30 million Tesla, it's 50 million Tesla. And this produces densities, because what happens is you've got this negative thing, and if there's any ions around, it will pull in the ions, and the ions and the electrons form this kind of plasma. It's kind of like a plasma, as Bostick called it, a plasmoid. And that these have a density that is equivalent to, in Lutz Jaitner's calculations, of a pulsar, i.e. a neutron star. This is very many orders of magnitude more dense than the center of the sun, okay? Oh. Now, when you have something that dense, you have something that if it's clustered in a certain way, then you get this monopole. And if you have a monopole, it's been well known that if you could ever see a monopole, these things will pull in electrons, but they'll also pull in ions. And the density and the pressure is so intense that it can cause proton decay. And proton decay is far, far, far more energetic than fission or fusion. Right?
Yeah.
Now, the reason I'm arguing this at this point in our conversation is that I've got this book here, and it's called Discover Cold Fusion. It's just out now by Ruby Carrot and Matt Hayworth. And in here, it describes something that happened to Martin Fleischmann and Stanley Pons a few years before their infamous presentation in 1989, March the 23rd, 1989. And there's a little sketch here. I don't know if you can see that your viewers won't, but there's the sketch.
Yeah.
And essentially what happened was they had a 1 cc of palladium, a little cube, I think it was, or a sphere. A sphere would be more ideal, but a cube. And let's say it's a cube. And then they were loading it for, say, 3 weeks with deuterium oxide, i.e. heavy water, electrically. And nothing was really happening. And this is the case. It takes a long time to do these particular type of LENR experiments. And what happened was nothing happening. They asked someone to go in and to turn the voltage down, and this, in my understanding, lowers the electrostatic pressure, i.e. the desire of the deuterons to go into the palladium. And then they start to come out. There's a flux out of the palladium because there's less pressure pushing it in, and this causes friction, fractures rather, in the palladium. That causes charge separation, according to Ken Shoulders. The charge separation creates these exotic vacuum objects. The exotic vacuum objects take the monoatomic deuterium and assemble these plasmoids. And what actually happened was, when they came in the following, I think it was on the Monday. It happened over a weekend, I think. Someone might be able to correct me on that. But the entire water container where the whole experiment was being held had basically been heavily displaced. It's a euphemism for exploded. But instead of it going in all directions, what happened was the whatever it was had gone through the glass of the container, through the lab bench that it was standing on, and made a fist-sized hole in the concrete. And
Wow.
there were particles. The whole environment was had a suspension of particles in the air.
Wow.
Right, and this scared them so much that they decided never to use such a large, this is 1 cc, it's 1 centimeter by 1 centimeter by 1 centimeter of palladium. Now, if you can imagine, you have a monopole, and the monopole gets to a strength where it can suck in the electrons, and then it can take in the palladium. And the palladium, let's say it's got a reason to go in there, it's an ion, then it gets disassembled and it feeds the beast, as it were. And that would go into the ground, and it almost doesn't matter. In fact, my understanding now of this technology is that to keep this thing running, you need to keep it in a metal. But it'll get locked in a metal because it can't move anywhere. And you can then trigger it you can give it scalar waves, or you can give it sound, or you can give it light, anything to cause it to move around, and it'll eat the matter that it gets moved to, or the matter that is able to impinge on it. And there was this researcher called Stanislav Adamenko, and he learned the Russian method of cold nuclear transmutation from the 1950s method. And by the late 1990s, he had managed to find an investor, and I think in 1998 he agreed to take over the lab outside of Kiev, the old nuclear isotope lab outside of Kiev in the Ukraine. And in 2000, I think, or 2001, he ran their first experiment. And this was at a lab called the Proton 21 lab. And they had what they call it's a dielectric barrier discharge, but it's a relativistic discharge. So it's reaching good fractions of the speed of light, the electrons. And it's a large pulse of electrons, ideally as monochromatic as possible, i.e. they are at roughly the same energy as each other. and they have a bucket of sort of aluminium oxide, alumina, and they have a special inductive piece of metal. And in their papers, I think from 2006 or 2007, they describe this quite clearly, how they have a capacitor bank, they discharge it, inductively held it in the metal, and then there's a plasma bridge which breaks the connection, the discharge path, and it can only discharge through the sample. And they have a sample like of a piece of copper, a little spike of copper, and then they have a disc of pure copper as an accretion disc. So the electric beam comes from this kind of flat piece of alumina, and it comes down and it all gets directed like many simultaneous lightning strikes of electrons at the same high energy go into this little spike, and in the spike it explodes, and they see every element in the periodic table coming from one element, and it almost does not matter what element you put in, right? And this experiment was run with something like 100 scientists for 6 years, so 600-man years. And every time they ran the experiment, they had transmutation, and they published this book. You can go and purchase it. It's not cheap. I think it's about $170 or something. It's 700 and something pages, so I guess it's good value per page. But it's very well described, their experiments and what they observed. And this was then moved to the US with the former founder and editor of Fusion Technology, I think I'm going to get this right, George Miley. I think I'm right in saying that. So and he that has now been moved to Oak Ridge at the moment, and they're looking to produce fusion energy with that technology. But in 2006, on the American Anti-Gravity site, there was an interview with I think it's Tim Ventura on there, and he describes this strange observation that they had on some of the accretion disks, and I think this one was copper, and they observed this thing where they have this thing called a secondary ion mass spectrometer, and what they do is they were firing cesium-133 ions at the disk, and the idea is that these come in with such high velocity they smash onto the disk and they spray off fragments, which atoms of the material that's on there. So then they use the drift velocity to work out which atoms have been created at that point. So it's a way of analyzing your material. And in this particular instance, they were shooting at this particular area on this accretion disk, and they weren't observing any secondary ions. And they thought, well, this is just completely bizarre. There's definitely something there. We can see it's there. We take it out and it's physically there. We can see it with our eyes, and we put it into the plate. Why can't we see anything when we're shooting at this particular structure in the plate? Well, what they then realized was that they weren't even observing the primary ions of cesium-133. And this is absolutely incredible, because normally so many ions of the cesium-133 get sprayed off that they cause the phosphor on the detection unit to glow, and they have to turn it off and kind of effectively kind of degauss it, but like let it calm down before, otherwise you get burning. And so they when they turned the power off, they noticed that in the center of this area where they weren't getting primary or secondary ions, there was a glowing spot which decayed exponentially. It was emitting light or something. And so they then did it again and then turned it off the power, and they saw this glowing spot. So it was consuming. It was consuming the matter that was being shot at it and not emitting anything. Wow. Now, that can only be, in my view, two things: a black hole or a monopole. And so, and now there's another case of a guy called Francesco Piantelli, and in August he discovered the nickel hydrogen condensed matter nuclear science experiment. This is in August 1989. But in 1994, he was running an experiment in nearby Siena University with a colleague from Bologna University, who's a very famous nuclear scientist called Sergio Ficardi. And this experiment suddenly started producing an unbelievable number of neutrons. So many neutrons that the lab was untouchable, the moderation blocks were now useless, and so forth. And so this was pretty scary for him. Now, a long time later, he told us when we were invited to visit him in 2015 that what was occurring was that this metal rod was ejecting protons. It was ejecting protons. And those protons were interacting with vanadium-50 in the choice of steel that he'd used to build the reactor. And the vanadium-50 causes a reaction. It's a known kinetic nuclear reaction that produces a neutron. So this is where the neutrons were coming from. He determined that by gold activation. Anyway, the nuclear authorities came in and they dealt with it, and this particular piece of nickel rod, and I saw it. It's about 10 centimeters long, and there was about a 5 to 7 millimeter section where all of the activity was going on. And he took this after he got it back 2 weeks later, and he put it into a cloud chamber. The cloud chamber is probably at minus 40 degrees centigrade, and what was coming out were protons. This is 2 weeks after the experiment had finished. And he's putting it into the cloud. And protons don't normally come out of matter. You get neutrons, you get beta particles, you get gamma rays, you get X-rays for radioactive materials. You don't normally get protons coming out. However, if you have something like a magnetic monopole or a black hole's analog, okay, and you have matter going in there for whatever reason, just a bit of Brownian motion, and gets within the event horizon, then you have a scenario where if you've got atoms fusing together, and they want to occupy the smallest space possible, well, they have to be a boson to form a bosonic cluster in that nucleus, that thing that's trying to squeeze it into a very small box. But if you're squeezing things together, but you've got a spare proton, it's a fermion, so it can't occupy that space the same as all the other bosons can. So it gets spat out. Right. And it gets ejected. And he actually has his whole patent and technology based on the fact that these protons get ejected, I think with up to 6.7 mega electron volts. And this allows you to do the original nuclear transmutation that was observed by Cockcroft and Walton in 1932, and which proved Einstein's theory that you can use this, and where they took a proton and they fired it into southern lithium. It goes to beryllium-8, which is a kind of fusion, but beryllium-8 is not unstable, so it decays to 2 alpha particles, which regain their electrons and become helium. And so this is one of his preferred ways to make power. You have the nickel. It's been treated in such a way that it is able to produce these ejected protons, and those go and interact with a secondary material. It could be something like boron 11, and that goes to carbon 12. So these are aneutronic reactions. So what's happening is there is a burgeoning understanding of how these nuclear systems are working, and there are many theories that are not possible. There are many theories that are a subset of the overall theory. As I said to you when we started out, it couldn't possibly be the case that all 130 theories were correct. Right. And it may be the case that what I'm suggesting now to you is not the whole story, or is only part of the story, or is a partial misinterpretation of the story. But the beauty of these structures, and there's a very key researcher in this field. Unfortunately, he died in 2013, as Ken Shoulders did as well. But he is a Japanese scientist from Sapporo. He's a nuclear scientist, and he immediately started on this cold fusion journey. And he found that he would produce these rings or these mesh clusters, and these things would produce things that would look like black holes or whatever. And he had these transmutations. Now, what would happen was he would have a piece of palladium and it would be loaded with deuterium. He'd run experiments, he would see excess heat and so forth. And then he would take the palladium, he would saw it in half. And inside the center of the palladium, he would observe that crystals of palladium had been eaten away inside the center of the palladium. And that around these areas which the crystals had been eaten away, there were transmutations of elements. Okay? Now, what would happen if you cause a proton decay? Well, you get muons coming out, and they decay extremely quickly into a muon, neutrino, an antineutrino, and an electron. I think that I might get that wrong, but it's very quick. So you get an electron out, which you might be able to use to produce, power, and you get this. You may get a monochromatic neutrino, which may be helpful, but those type of relativistic neutrinos don't interact very well, as people will know. You need light years of lead. And then you have a muon, and the muon can go on to catalyze muon-catalyzed fusion, which muons like much, much heavier, like 207 times the weight of an electron. And so when that replaces an electron in a deuterium molecule, that brings the two deuterons so close together that they can fuse, and that produces energy, and the muon gets released and it goes on to do another fusion. So this is that the muon doesn't disappear. It goes around with a lot of muon, with a lot of deuterium atoms, and fuses them. So this is called muon catalyzed fusion. And at the time, this was the theory of how cold fusion worked by one Stephen E. Jones. And Stephen E. Jones was the person that put up his hand in 1989 and said, I think, to the assembled 6 other scientists, who thinks that this science isn't a real thing or whatever, and basically put an end to the Pons and Fleischmann initial stories. It says here in the comic book here that I'm reading, it says, who here thinks there is no merit at all to the Pons and Fleischmann process? And he put up his hand, like predisposing their output, and all that, I think one put up their hand. So he was basically in competition at that time with Pons and Fleischmann. Now, the interesting thing is right now is there's a guy called Leif Homlid. He's a scientist that works at a Swedish university. And he's observed that he can create this thing called an ultra-dense hydrogen and ultra-dense deuterium. Now, you could argue how these are ultra-dense. I would suggest that it is these structures that I've been talking about before that causes this production of these ultra-dense structures. But anyway, when he fires a laser at these ultra-dense structures, he gets flashes of muons that he has observed being produced. Now, you wouldn't, at the same time as muon production, you will also get pion productions, which are like the bits out that come from the center of a proton decaying. And these would go on to cause wide-scale transmutation, just as observed by Takaaki Matsumoto. But these muons, he's observed them like every day of the week. And there's I think there's a researcher in Norway that's replicated this, and I think there's another researcher in Iceland that may have, I'm not sure about that, but they're certainly working in his team. And they've got a company called Norrent Fusion to look to commercialize this technology. But what I'm trying to say is they've started off with deuterium. They've got a catalyst, which is I think it's like a dehydrogenation catalyst and used to make styrene and things like that. This has potassium in it, which is absolutely critical in many of these technologies, just as it was critical to the alchemists of yore. Yeah. And there's a very good reason for that, and I can expand upon that. Basically, he is observing proton decay, and the output is muons. So it could be the case that both Stephen E. Jones and Pons and Fleischmann were correct.
Well, very good. Well, this is so exciting because I really love the story of Martin Fleischmann and Stanley Pons and the work that you're doing. And quick, when do you think, I know we're fast forwarding because there's a lot more we need to unpack together, but when do you think, I mean, knowing what you know about the field, when is something going to come to market with the LENR cold fusion? Like, is it 10 years out, 5 years?
I think if 15? There hadn't been such a reputation trap and disinformation campaign, I think it would have happened before the end of the 1990s. Certainly, Takaaki Matsumoto was very close, as were others. There's a Russian researcher called Solin that had an awarded patent that produced transmutation, and a 2001 application that was refused by the US Patent Office, which produced direct electricity. So this could have all happened 2 or 2.5 decades ago.
I feel like we're living in artificial dark ages when I hear stuff like that.
Yeah, I know, but this is the problem. The idea of proton decay, which is specifically named in the Russian patent of Solin, that was awarded in 1997 with a priority of 1992. He describes magnetic charges, exactly the same transmutations everyone's observed, and he says proton decay. He says it right there in his 1992 application. So this was all known in prior to 1992. So the real barrier here is that no one who has really got a clue is matched up with the people that have got the finance to make it happen in a scenario that's going to allow it to happen, given all the vested interests that would want to stop it.
Wow. Well, let's leave it there. That's a very good way to leave it. That's the practical rubber meets the road part of this conversation. So, Bob Greenyer, I really appreciate your time. And where can people find your work as they want to continue to follow you. We'll pick up soon, but for now, what's your
I,
website?
I would go to the Martin Fleischmann Memorial Project YouTube channel. We have a website where we had a lot of the historical research that I was talking about, and some that I haven't even addressed, where we shared all the data live and protocols. That's at quantumheat.org. And if you look at our recent videos, you will see some of the things that I've been discussing. And there's a killer video coming out in the next few days, which I think I would really encourage your listeners to look out for.
And I want to see those glowing toroidal. Can you show me the video for that? The toroidal structures that were glowing and spinning. I want to see that.
I can't show you right now, but it is on. If you look up Bogdanovich on our YouTube channel, you'll be able to see the and gain access to the links to the published papers.
Very good. This is very exciting stuff, and we'll continue soon. So thanks for your time.
Thank you very much, and it's been a pleasure speaking to you, David.
Very good. Thank you.